So in this video, I will be continuing with PHS 2021 4E Pure Physics paper. So in this video, I will cover question 7 and I will cover question 8 and 9. So it will cover the whole of, that will be the end of section A. So question 7 is your very typical refraction, Snell's law kind of question. So whenever teachers set this paper, right, we always want to check whether students remember that all your angles has to be measured from the normal. This is one thing we always like to check. The other thing that we want to check is that we want to know whether you are aware to compare the incident angle with the critical angle. This is to check if total internal reflection will happen. So let's see how PHS check our understanding. So first, as you can see, they ask you to measure the angle of incident and they didn't give you the normal. So please be very careful. You are supposed to measure this angle, the one in blue. So after you measure it, remember all your values in your theory paper 2SF, and it is in degree. Please check for your answer, okay? Please check for your unit, not answer. Okay, then after that, they ask you to actually find the angle of refraction in the glass block. So they are asking you to find this red color angle. And they gave you the refractive index of the glass. Yeah? So you can apply your Snell's law. Some of you all like to use the short form sin I over sin R. You will find that sometimes it works, sometimes it doesn't. So I only teach my student to use Snell's law, the full form. So Snell's law, very easy. One side will be glass, the other side will contain all the data for glass. One side will contain all the data for air, the other side will be using the data from the other medium. So in this case, I think I have completely missed it because on this side, because 1.6 1.6 is the data for glass. So this should be glass, I'm so sorry. And in the glass, I would have this angle of refraction. So I call this capital R. Then on the air side, my refractive index for air is 1. And the angle that is in the air is actually from part A. So if you go and substitute that into this, you should be able to find the angle of refraction. So just a reminder, even in degrees is 2SF, and I have shown you the Marcus report showing that for angles it is also 2SF if you remember. If you don't remember and you want to prove, PM me, I will be very sarcastic, but I will still show you. Okay, Ken? For part C, you're supposed to check whether the ray will emerge on side BC. So side BC, it is over here. So I already have drawn the ray, but for you, you need to draw it to scale. So you need to find out what is the angle of refraction, and then you must draw this ray accordingly. Now, once you know that this red color angle is R, you can actually work out the green part. So the green part over here will definitely be 90 degree minus R. So this 90 degree minus R will be your angle of incident when your light strikes the boundary BC. So this one is the angle of incident that you will need to compare with the critical angle. So down here, like how I have written here, if you see that there is light traveling from a high index to a low index, you must check for TIR. And the way to check for TIR is that you need to compare the incident angle at which the ray is striking the boundary BC. In our case, this is the green angle. And you compare this with the critical angle of that particular medium. In this case, we need to find out the critical angle of the glass. So how to find critical angle of the glass? You have to imagine that this is the glass and there's a ray striking the glass air boundary or whatever boundary you have, and then because it is at critical angle, the ray will actually go along the boundary. So you need to set up this mental picture in your mind that when the ray strikes the boundary at the critical angle, the purple one, the light will actually bend along the boundary of the medium. Then after that, you can apply your Snell's law. So the air side, refractive index of air is 1. In this case, this is air, right? So the angle in air is actually 90 degree. And for our glass, right, I already know its refractive index is 1.6. In this case, we have light that is along the boundary, so I know that the angle over here must be the critical angle of the glass as it is defined. So using this setup, you will be able to actually find out that the critical angle is 38.682. This is like the passing mark for the glass block lah. So your incident angle is like your grade. So you score, let's say 60 degree, and then you compare with the critical angle. Oh, okay, it is more, so I pass, right? So in this case, for the explanation, there are a few that you can offer. If your angle I is equals to or very close to critical angle, then obviously your ray is going to bend this way, right? If your angle of incident is larger than the critical angle, then this phenomenon called total internal reflection will happen, and basically these two angles will be the same. It follows the same rule as a reflection. Lastly, the other possibility is that your angle I is less than your critical angle. In this case, when you shine the light in, it will just get refracted away normally, like how a normal refraction happens. So since it is 3 mark, you need to of course tell us which scenario it is, and then you can then make a conclusion. Okay, for part 8, it is a simple DC circuit. Notice that I have lamps of identical R. So actually I like to put all my information in one place. Okay, I have a 4.5 volt battery. There's a switch S. So for switch S, now switch S is closed, so that's why I drew this line. So when switch S is closed, you can see that lamp X and lamp Y is in parallel. That's why when you are asked to find total resistance, you have to deal with this first. So combine X and Y by the parallel connection formula. Then after that, X and Y, after you combine them, they will be in series with Z. That's why you can just sum it up like that. So your total resistance is given by this. Now usually when you are doing part B, you have to use some of the information in part A. So in part A, since I already know my total resistance, I can actually apply V equals to IR to the whole circuit. So R of the whole circuit is 7.5 and V of the whole circuit from the battery is 4.5. So what I have found out is actually the main current. The current coming out from the battery will be 0.3. And because the current coming out from the battery is 0.3, that will allow me to actually find 0.6, right? 0.6 right here. Yeah, the current from the main branch is 0.6. So now I know that this main branch is 0.6. So this main branch will go to here when it will split. And because for both paths the resistance is the same, that means my current will split 50-50. So I know that this is 0.3A, this is 0.3A. So that's how I get it. And remember 2SF, very important. Okay, for part C, now that the switch is open, what will happen to the potential difference across X and Y? So potential difference refers to the voltage. So here I have redrew the circuit here for easy reference. So I have opened up the switch, and what I have done is that this yellow path, now I turn it green, is how the current will flow. And you can see that the current only flow through light bulb Y and light bulb Z. So because of that, this means that the I have calculated in B cannot be used, because now my total resistance has already changed. Initially it involved both X, Y and Z, Now that the switch is open, it only involves Y and Z. So once I know that, this green color path, basically it is a series. So if it is in series, right, if Y and Z is in series, then I know that the EMF is going to be shared by X and Z equally. Why equally? Because the resistance is the same, because identical lamp. So once I know that they are the same, I would be able to tell that, oh, my EMF is 4.5, I share it equally, it will be 2.25 each. So it means that when my charge move out from the battery and come to this place, the charge will carry 4.5 volt, right? After this charge go past the light bulb at Y, the charge will left with 2.25 volt. Same thing, after 2.25 volt pass through the Z, I will be left with 0. So now that I have all the voltage at different point, you can then solve the question. So for example, I want to know potential difference across X, right? I want this, right? So potential difference across X, I need to put my voltmeter like this, right? One arm on the left, one arm on the right. So it's like hugging onto X. So you can see that this particular arm will receive 4.5, and this particular arm, well, did the charge lose any will there be a current flowing through this path? There will be no current flowing through this path, right? No I. So once you know that there's no I, it means that there must not be any potential difference, right? So actually the charge here still have 4.5 volt, the charge here still have 4.5 volt. So the potential difference here will actually be 0 volt. Okay, so potential difference across X is actually 0 volt. Okay, then after that you want the potential difference across Y, so you will put your voltmeter like that, right? And you can see that this arm on the left will get 4.5 volt, this arm on the right will get 2.25 volt, and as you see, the PD will be 2.25. So 2.25, round it off to 2SF, and you will get that. Last question of section A is about magnetic field. So this question basically is either you know or you do not know. So for question 9, you can see that at X, the field is very uniform, and at Y, it is bulging out slightly. Okay, so what does a parallel and uniform field means? Well, it means that the field is very strong, and it is very uniform. That means everywhere is almost giving you the same strength. Now at Y, because it is already bulged out, it is relatively weaker and less uniform. Last question, I suggest you check the textbook on the definition on what is meant by North Pole. Offhand, this is what I can think of. Okay, so do leave a comment if you have